we continue on with our discussion on space with the effect of Earth's rotation on launch. So before we start looking at the effect that the Earth's rotation has on launch, we're going to have a look at the Newtonian idea of the law of the addition of velocities. If we have a runner here, and that runner is running at 5 meters per second, and that runner holds a ball, and the ball is in her hand here, then the ball is already travelling at 5 meters per second. If we then throw the ball further forward at 3, then the ball would not be just travelling at 5, but it becomes 5 plus 3, and the ball travels forward at 8. So the two velocities add together, and this is one of the reasons why we take run-ups in cricket. The bowler runs firstly as fast as possible and then throws the ball forward, and therefore the addition of the ball's motion forward and the runner's motion makes the ball travel faster. Now we're going to take this principle and use it when we have a look at why we launch towards the equator on the Earth, because on the Earth's surface, the Earth is not travelling at a specific speed all over its own surface. So just taking a few moments for a second to have a look at this. Here is the Earth. And we'll put firstly the poles on the Earth. So here's the North Pole up here, and then the South Pole down here. And we'll just say we rotate like that. Let's put the equator on here. And let's have me standing here on the equator. Let's put somebody else up here on the Arctic Circle. I'll have him standing up there. Now, the Arctic Circle is a circle about that size on this diagram, whereas the equator, the equatorial circle, will be much bigger, and there's part of it there. Now, if we use 2 pi r, we know that the circumference of the equatorial equator is much larger than the radius, the circumference of here, because the radiuses are bigger. Okay? So, the Arctic Circle's travel, the person will travel around the Arctic Circle in one 24-hour period. At the same time, a person will travel around the equator on a 24-hour period. Therefore, this here, if you're travelling on the equator, you must be travelling at a much faster speed than you would be if you're on the Arctic Circle. And we know that if we are on the equator, then the Earth is travelling with actual rotation is around about 17,000 kilometres per hour, rounded to an easier number to remember. So before the rocket is even launched into space, it's already travelling eastward at a very high speed. Now the reason why it's travelling eastward is that though the sun appears to rise in the east, the Earth is actually spinning towards the east, making the appearance that the sun is rising in the east. And we're going to use this extra speed to help us put a rocket into space or into orbit. Now remember, we need velocities around about 7,000 metres per second or 11,000 metres per second for for orbital and escape velocities. So for a normal escape velocity, it's 11,000 metres per second. That's for escape. And for just normal day-to-day orbits, they're approximately in the order of 7,000 metres per second, 7 kilometres per second. So these are very hard speeds or high speeds to achieve. So we're going to take advantage of the actual fact that we're already partway there because the Earth is rotating. So here's a diagram of the Earth rotating in this direction here. So when the path of the launched vehicle will go this way, it will go in this direction here, rather than in the opposite direction. So we're going to already take part of the rotational motion of the Earth to increase our velocity so we can use it to get into orbit much more simply. And in this case, we use much less fuel. And if we're using less fuel, the costs are decreased for launches into space. So, to summarise, we launch in an easterly direction to take advantage of the natural rotation of the Earth. If we were to do it against the motion of the Earth into a westerly direction, then we need extra energy, and this becomes extra fuel. Extra fuel is extra costs. So rockets are simply launched in an easterly direction to take advantage of our spin, the Earth's spin. Not does the Earth just spin, the Earth is turning like this on its axis, but it's also turning on its, going around in an orbit.
Right. Well, compliment.
Yeah, just got to need to